In the previous video, we introduced the concept of PI control, which can be used to eliminate the observed steady-state offset that often arises when proportional-only feedback control is used for self-regulating processes. PI control does not respond more quickly to rapid changes than to slow changes in the error signal or in the measured value. This can be remedied with what we call PID control. PID control also uses the derivative of the error signal in addition to the integral of the error signal. The derivative element of the controller is designed to respond to the rate of change of the controlled variable. Consider the response of the integral element of a PI controller if the controlled variable is deviating slowly. The magnitude of the integral element response to changes in the controlled variable is represented by the area shown here. By the time the error signal reaches a value E1, this area is large. However, for a more rapidly changing controlled variable, the error signal reaches the value E1 when the integral element, or the area under this curve, is smaller. This means that the integral element will actually respond more slowly to fast changes in the controlled variable. That's sort of the opposite of the type of response that we want from a controller. We would rather have the controller respond more quickly to fast changes and more slowly to slow changes. The solution to this is to include a derivative component in what we call PD control if we have only proportional and derivative control, or PID control if we have proportional, integral, and derivative elements in the controller. For a PD controller, the deviation in the controller output is proportional to both error signal and the derivative of the error signal. Here, tau d is called the derivative time. We can take the Laplace transform of this equation to find the corresponding Laplace domain equation describing the PD controller. Remember that taking a derivative in the time domain corresponds to multiplying by s in the Laplace domain. The transfer function for the ideal PD controller is then found by dividing this equation by the error signal. In practice, the ideal PD controller is not actually physically realizable, but this controller can be approximated by adding a first-order denominator to the derivative term in the transfer function. This corresponds to what we call a first-order filter on the derivative element, which we'll see is actually quite useful. The reason that the ideal PD controller is not really physically realizable is because it requires instantaneous knowledge of the derivative of the error signal, and we cannot instantaneously know the derivative of the error signal without knowledge of where it is going in the future, or in which direction the error signal is changing. We can only know instantaneous values of the error signal. This first-order filter that appears in the denominator of the derivative element can reduce the sensitivity to noise in the error signal. PD control is actually not used very often. Often, rather, derivative control is implemented as a PID controller. In the time domain, the PID controller calculates the output by adding the bias to a term that's proportional to the error, proportional to the integral of the error, and proportional to the derivative of the error. This can be represented in the Laplace domain by the block diagram shown here. The error signal, its integral, and its derivative are summed, and that sum is multiplied by the controller gain Kc to compute the controller output. Remember that in the Laplace domain, multiplying by 1 over s is equivalent to taking the integral in the time domain, and multiplying by s is equivalent to taking the derivative in the time domain. The transfer function for the PID controller is a linear combination of the proportional controller, the integral element, and the derivative element. To understand why we use PID controllers, let's consider how each individual element would respond to a deviation in the controlled variable like the one shown here. Initially, the controlled variable is at its set point, but then it begins to deviate with a linear ramp. Then the controlled variable remains at a constant sustained value away from its set point. Let's consider how all three parts of the PID controller will respond to this error signal. At point 1, the proportional controller thinks, this isn't too bad. The controlled variable is deviated from the set point, but it hasn't deviated by very much. Similarly, the integral element, only sees a small area under this curve, so it doesn't think that this deviation in the controlled variable is very serious. However, the derivative element measures the slope of this line. The derivative element is quick to identify that there is a problem, and the steeper this slope, the more serious the problem must be. By the time we get to point 2, the proportional element has increased from point 1. Now the proportional element is getting more serious about responding to the error. The integral element is now responding to the area under this curve and thinks things are getting really bad. However, the derivative element sees the derivative of a flat line, which is 0. So the derivative element stops responding when the error signal stops changing. At much later time, indicated by the 3 out here, the proportional element doesn't know that anything is any worse than it was at point 2. But the integral element is getting very excited because this area is getting larger and larger. And the derivative element thinks that everything is fine because the derivative here is 0. So at different points during the progression of this error signal, these different elements are responding differently. The derivative element responds well at the beginning, and the integral element has an increasing response as the controlled variable stays far from its set point for an extended period of time. So while derivative control found the problem first, it cannot respond to a flat error signal. For this reason, probably 90% of the controllers that are used industrially are some form of PID control. In the next video, we'll take a look at some general trends of how PID controllers behave when they're installed in feedback control loops, by seeing some general features of how controlled variables respond.